Welcome to the Deep Dive. We're the show that really tries to cut through all the noise and just pull out the key insights, the important stuff from a whole stack of sources. And today, wow, we're diving headfirst into something that's just fundamental to how we experience the world, something you do thousands of times a day, probably without even thinking about it, how we interpret everything we see around us. I mean, think about it for a sec. You spot a friend's face in a packed room like that, or you know instantly if that thing coming down the street is a big bus or just a car. Or maybe spotting a tiny bird hidden in the trees. It feels effortless, right? Almost magical. We totally take it for granted. But getting machines to do that for the longest time, that was this huge, almost impossible challenge. And the breakthrough, the thing that really made that monumental leap possible, well, it was largely down to one really revolutionary invention in AI. Convolutional Neural Networks. So often you hear them called CNNs. So our mission today is to take you on a journey through this incredible revelation that CNN sparked in AI. We're going to trace where they came from, starting with some fascinating biological inspiration. Then we'll get into exactly how these networks manage to see the world, how they interpret all this complex visual information, layer by careful layer. We'll explore the massive impact they've had and continue to have on so many parts of our daily lives. And hopefully by the end, you'll really grasp why CNNs are still considered one of the most significant game-changing inventions in AI history. We'll follow the story, starting with Yann LeCun's really pioneering work on LeNet back in the 90s. That was what first showed the potential. Then we'll jump to the 2010s, the era of AlexNet and ResNet, when things really exploded. We're going to try and demystify how these networks manage to mimic, in a way, our own visual cortex, how they recognize features step by step, hierarchically. Starting with simple things like lines and edges, then building up to shapes, and finally whole objects and scenes. And yeah, we'll definitely highlight their role in stuff you see all the time, like facial recognition on your phone, but also in critical areas like medical imaging, and of course the whole push towards self-driving cars.
Yeah, and it's really crucial to set the stage here, historically speaking, because early AI, it had some quick wins. It was pretty good at solving logic puzzles, playing games like checkers, things with very clear rules. But when it came to tasks that needed to deal with the messy, unpredictable real world, like pattern recognition, seeing things, it really struggled. The field actually went through these periods called AI winters, you might have heard of them, basically times when the hype got way ahead of the reality. Grand promises were made, funding poured in, but the results just didn't materialize as quickly as people hoped, leading to disillusionment, funding drying up. It happened a couple of times. Even early artificial neural networks, which were conceptually trying to mimic the brain's structure, lots of interconnected neurons, they also had these boom and bust cycles. The ideas were there, maybe, but the expectations were just too high for what was possible at the time. Primarily, the raw computing power just wasn't there yet. And maybe even more importantly, the enormous amounts of data you need to train these kinds of models effectively. They simply didn't exist, not in any accessible way. So these two things, hardware limitations and data scarcity, they were massive roadblocks. Even brilliant theoretical ideas couldn't really overcome them on their own back then.
All right, so before CNNs really took off, just getting a computer to reliably see anything was this incredibly tough nut to crack. Just imagine trying to write a program, like a traditional program, to identify a cat. It sounds simple, but think about the sheer variety. You've got Persians, Siamese, tabbies, endless breeds. Different colors, obviously. And there's lighting, bright sun, shadows, indoors, outdoors. And the angle. Is the cat looking at you? Sideways, from above. What if it's partly hidden behind a sofa? Or, jumping midair, maybe even upside down for a split second.
Exactly. The variability is just immense.
And the traditional methods, the ones based on writing explicit rules for every possibility, they just completely fell apart. They couldn't handle that complexity. It was kind of like trying to teach someone to read by giving them a dictionary with every single possible way every letter could ever be written. Not just A and A, but like A in cursive, A typed in Arial, a slightly smudged A, an A drawn by a kid with crayon, an A half covered by a coffee stain.
It's an impossible task, just
Yeah,
not scale.
totally. It was incredibly brittle. You change one little thing, the lighting shifts slightly, and the whole system breaks. It just didn't understand what a cat was. It only knew the rules it was given.
And the visual world is far too rich and dynamic for rules alone. You need something more flexible, something that can learn. And what's really cool, almost poetic, is that the big breakthrough didn't come from writing even more complicated rules. It came from looking inside ourselves, at our own biology. CNNs are directly, profoundly inspired by the best visual processor we know, the human brain, specifically the visual cortex. Our brains are these incredibly complex biological neural networks. We're talking roughly 100 billion neurons, give or take.
Staggering number.
It really is. And each of those neurons connects to maybe 1,000 others through these junctions called synapses. And it's the strengths of those connections, the patterns they form, that encode pretty much all the information, allowing for learning, memory, complex thought.
So the goal became essentially replicate that kind of structure, or at least the principles of it, in silicon. But how does our brain specifically handle vision in a way that sparked this idea?
Right, so the key concept here, particularly relevant for CNNs, is something called hierarchical processing. It happens in the neocortex, the part of the brain doing the higher level thinking. Visual information isn't just processed in one big lump. It's broken down and analyzed in stages, in layers. It moves from very simple, basic features to much more complex and abstract representations.
Layer by layer.
And think about seeing a familiar face. Your brain doesn't just get a blob of pixels and instantly say, oh, that's Sarah. No, it starts simpler. First, maybe it detects basic lines, edges, where light meets dark.
Okay.
Then the next layer might combine those lines into simple shapes, the curve of an eyebrow, the oval shape of an eye. Then those shapes get combined into parts, a nose, a mouth, 2 eyes. And finally, those parts assemble into the whole face, which your brain recognizes as Sarah, pulling up all the associated memories and feelings. It's a hierarchy of understanding built up step by step.
That makes a lot of sense. It's like building blocks.
Exactly like building blocks. Or consider how memory works. You might see your grandmother, sure, but maybe a specific smell, like baking bread, or a certain song, or even just an old chair she used to sit in can trigger that memory just as strongly. Your brain doesn't have just one single grandmother file. It's built this incredibly rich, interconnected, hierarchical web of associations and patterns. It can recognize the concept from many different starting points, and that powerful pattern recognition, that hierarchical structure, is fundamentally what inspired the architecture of CNNs.
That's a really clear connection. And this biological inspiration leads us straight to a key figure who really started to make this work in practice, Jan LeCun. And his work on LeNet back in the 1990s, LeNet wasn't just, another small step. It was a really significant early convolutional neural network.
Yeah.
Kind of laid down the blueprint for so much that followed.
Absolutely, it was foundational.
The core idea was, well, pretty elegant. Instead of trying to feed the whole image into a network at once, which is super computationally expensive and doesn't generalize well, LeNet introduced these things called convolutional layers. The idea was to scan the image with lots of small filters or kernels.
Little magnifying glasses almost.
Yeah, exactly. Like little magnifying glasses, each one looking for a very specific, simple pattern, maybe a vertical edge or a specific texture or a corner.
And crucially, these filters share their weights. So the same filter looks for the same pattern across the entire image. That was a key efficiency game.
Right. And then after finding these basic features, LeNet used something called pooling layers. What was the idea behind those?
Pooling was mainly about reducing the amount of data, making things more manageable computationally, but it also did something really important. It made the network more robust to the exact location of the feature.
So it didn't matter quite so much exactly where the vertical line was, just that there was a vertical line in that general area.
Precisely. It provides a degree of what's called translation invariance. It helps the network recognize a pattern even if it's shifted slightly or scaled a bit.
Which is huge for real-world images because objects aren't always perfectly centered in the same size.
Exactly. Before LeNet, if you trained a network on a cat in the top left, it might completely fail if the cat appeared in the bottom right. Pooling helped overcome that fragility.
So LeNet combined these convolutional layers, looking for local features everywhere, with pooling layers to make it more robust and efficient. That really was a paradigm shift, wasn't it? It started to mimic how we process visual information at those early stages.
Okay, let's dig a bit deeper into this convolutional idea because it really is the heart of how these networks learn to see. You use the analogy of a small magnifying glass, a filter, or kernel. So imagine you're sliding this specialized little lens across the entire image, right, left to right, top to bottom. And this lens isn't just magnifying, it's specifically tuned to look for one particular thing. Like maybe it's designed to strongly react when it sees a sharp vertical edge. Right. Or a diagonal line, or a specific color change, or a texture.
So when that filter passes over a part of the image that matches what it's looking for, it produces a strong signal, a high number. And where it doesn't match, the signal is weak, a low number.
Correct. And doing this across the whole image with one filter creates what's called a feature map. It's basically a new image that highlights exactly where that specific feature was found.
And you don't just use one filter, right? You use lots of them in parallel in each layer.
Oh yeah, many. Each convolutional layer will have multiple filters, each searching for a different simple pattern. So you end up with a stack of these feature maps after the first layer, each map showing the locations of a different basic feature.
Okay, and you mentioned these filters define a receptive field. Can you explain that a bit more?
Sure, the receptive field is just the small, localized patch of the input image that a single neuron or single point in the feature map is looking at through its filter. It's like its little window onto the world.
So each neuron is only looking at a small piece.
In the early layers, yes. But here's the clever part. These receptive fields overlap significantly as you slide the filter across.
Ah, okay. So it's not like looking through separate peepholes. It's more like scanning with flashlights, where the beams overlap.
That's a great way to put it. The overlap ensures you don't miss features that might fall right on the boundary between two theoretical peepholes. It gives the network a much more continuous and robust view, capturing features effectively regardless of their exact starting position within that small neighborhood. It makes the whole process less sensitive to exact pixel alignment.
Got it. So that's the convolution part, scanning with overlapping filters to find basic features. Now, what about the hierarchy? You called it the ladder of perception. How does it build up?
Right, this is where it gets really fascinating. A CNN isn't just one convolutional layer, it's a stack of them, often interleaved with pooling layers, and those activation functions we'll get to. And each layer learns progressively more complex features based on the output of the layer before it.
So the first layer finds the simplest stuff.
Exactly. The very first convolutional layers are detecting really basic elements. Edges vertical, horizontal, diagonal. Corners. Simple blobs of color or texture. Think of a filter that's half black, half white. It's going to light up strongly wherever it crosses a sharp edge in the image.
Like finding the individual Lego bricks.
Precisely. Very low-level, fundamental building blocks of any image. They don't represent anything meaningful on their own yet, just basic visual primitives.
Okay, so layer one finds edges and corners. What happens in the middle layers?
The middle layers take the feature maps from the early layers, the maps showing where the edges and corners are, and they learn to combine them. So a neuron in a middle layer might learn to activate strongly if it sees, say, a horizontal edge feature map active just above a vertical edge feature map from the layer below. What does that combination represent?
Maybe a corner, like the corner of a box.
Yeah. Exactly. Or it might combine several short line segments detected in the previous layer to recognize a curve. Or combine certain textures and shapes. So if you're training a CNN on car images, these middle layers might start to recognize patterns that look like circles, maybe tires or headlights, or rectangular shapes for windows or doors.
So it's going from lines to simple shapes and parts of objects. Still not a whole car, but components.
Right. It's learning that certain combinations of the simpler features are statistically relevant, that they frequently appear together in the training data and likely represent something more meaningful.
And then the deeper layers. That's where the magic happens.
That's where it all comes together. These deeper layers take the combinations of shapes and parts detected by the middle layers and integrate them to recognize entire objects or even complex scenes. And this is where you see that remarkable phenomenon we touched on earlier. In a CNN that's been trained well, you can actually find individual neurons or small groups of neurons in these deep layers that seem to respond very selectively to high-level concepts. There was that famous study where researchers found specific neurons that reliably fired when shown images containing cats and other neurons that fired for dogs.
Even though nobody explicitly programmed cat detector or dog detector into the network.
Exactly. Nobody told it what a cat is. The concept of catness, this complex combination of shapes, textures, and parts, just emerged naturally from the network learning patterns and the vast amount of image data it was trained on.
Wow.
It's really profound. The network builds this compositional hierarchy. Edges combine into basic shapes. Shapes combine into parts like eyes or wheels. And those parts combine into complete objects like faces or cars. It learns the visual world from the pixels up.
That emergence of concepts is just mind-blowing. But for this complex learning to happen, for these layers to build useful representations, you mentioned It can't all be simple linear math. We need activation functions, right, like ReLU. Tell us a bit more about why they're so crucial.
Right. So convolutions and pooling are essentially linear operations, mathematically speaking. If you just stacked a bunch of linear operations on top of each other, the whole network, no matter how deep, could only ever learn linear relationships.
Like just drawing straight lines through the data?
Pretty much. It couldn't capture complex, curvy patterns. The real world is full of nonlinear relationships, and you need to introduce nonlinearity into the network to allow it to model that complexity.
And ReLU does that. How?
ReLU, the rectified linear unit, is actually incredibly simple but very effective.
Yeah.
All it does is, if the input to the neuron is positive, it lets it pass through unchanged. If the input is negative, it just outputs 0.
So it's like a switch.
Yeah.
On if positive, off if negative.
Exactly. It's a very simple nonlinear transformation. But inserting this simple switch after the linear convolution operations in each layer allows the network as a whole to approximate much, much more complex nonlinear functions. It lets it learn those intricate patterns and boundaries in the data that are essential for tasks like image recognition. Without nonlinearity, deep learning wouldn't be nearly as powerful.
Okay, that makes sense. So you've got the layers, the filters, the pooling, the nonlinear activations. But how does the network actually figure out the right values for all those filters? How does it learn? You mentioned backpropagation.
Ah, yes, backpropagation, or backprop. This was a truly crucial development, really popularized in the mid-80s by Rumelhart, Hinton, and Williams. It solved a massive bottleneck in training neural networks with multiple layers.
What was the bottleneck?
The problem was figuring out how to adjust the connections, the weights, inside the network, especially in the hidden layers based on the final error. If the network makes a mistake classifying an image, how do you know which of the millions of weights in the middle layers contributed most to that mistake and how to adjust them?
Kind of like assigning credit or blame through the whole network.
Precisely. Backpropagation provides an efficient mathematical method to calculate the gradient of the error with respect to every single weight in the network. It tells you how much changing each weight will affect the final output error.
Okay, and how does it do that?
It works by first calculating the error at the output layer, how far off the network's prediction was from the actual correct label. Then it propagates this error signal backwards through the network, layer by layer. Using the chain rule from calculus, it systematically calculates how much each neuron in the previous layer contributed to the error of the neurons in the current layer. It keeps doing this all the way back to the input layer.
So it figures out the contribution of every single connection to the final mistake.
Essentially, yes. It computes the gradient, which direction, and how much each weight needs to change to reduce the error.
And then you adjust the weights based on that. That sounds like the gradient descent idea you mentioned.
Exactly. Backpropagation is really an efficient way to compute the gradients needed for gradient descent. Stochastic gradient descent, or SGD, is the optimization algorithm typically used.
The Foggy Valley analogy.
Right. Imagine the error as the altitude in that foggy valley. Backprop tells you which direction is downhill from where you are, the gradient. SGD then takes a small step in that downhill direction, adjusting all the weights slightly.
And you repeat this process over and over with lots of images.
Thousands, millions of times. Each time the network sees an image or a small batch of images, it makes a prediction, calculates the error, uses backprop to find the gradients, and uses SGD to nudge the weights slightly in the right direction to reduce that error. Over time, the network learns to set its weights to minimize the overall error and become better and better at the task.
So backpropagation was the key that unlocked the ability to actually train these deep, multi-layered networks effectively. It turned them from interesting theoretical constructs into powerful learning machines.
Absolutely. It was a cornerstone algorithm for the deep learning revolution. So, okay, we had these key ingredients by the late 80s and early 90s, the convolutional structure inspired by Linnet, and backpropagation to train multi-layer networks. But, as we said, progress was still kind of slow for a while.
Why was that if the core ideas were there?
Mostly those two big limitations we talked about, compute power and data. Training these networks, especially as they got deeper, required immense computational resources that just weren't widely available or affordable. You needed huge labeled data sets to train them effectively, which also didn't really exist back then.
It was a bit of a waiting game for the hardware and the data to catch up.
In many ways, yes.
Yeah.
But then things started to change dramatically in the late 2000s and early 2010s. Computationally, the big game changer was the rise of GPUs, graphics processing units.
Originally for video games, right?
Exactly. They were designed to do lots of relatively simple calculations in parallel, which is exactly what you need for rendering graphics. But researchers realized that the core mathematical operations in training neural networks, especially matrix multiplications, were also highly parallelizable.
So they repurposed gaming hardware for AI research.
Pretty much. GPUs provided a massive speedup, sometimes orders of magnitude faster than traditional CPUs for these specific tasks. Suddenly, training much larger and deeper networks became feasible. It was like going from a bicycle to a sports car for AI computation.
Okay, so the compute barrier started to fall. What about the data barrier? This is where it gets really exciting. This brings us to the ImageNet project and the associated competition, the ImageNet Large-Scale Visual Recognition Challenge, or ILSVRC. This was spearheaded by Professor Fei-Fei Li and her team.
A truly monumental effort.
Absolutely. ImageNet wasn't just a data set. It was the data set that changed everything for computer vision. You're talking millions of images, all meticulously hand-labeled by humans, covering over 1,000 distinct object categories.
Everything from different breeds of dogs, types of mushrooms, cars, tools, you name it.
The sheer scale and quality of ImageNet were unprecedented. It finally provided the massive, diverse, labeled dataset that deep learning models desperately needed to learn effectively and generalize to real-world visual complexity.
It also created a common benchmark, a really tough competition that spurred incredible innovation. Teams from all over the world competed to build the best image classification models.
And this leads us directly to 2012, a watershed moment.
Yes, 2012. That was the year AlexNet arrived. Developed by Alex Krzyzewski, Ilya Sutskever, and the aforementioned Jeff Hinton at the University of Toronto. AlexNet was a deep convolutional neural network, much deeper and wider than LeNet, leveraging GPUs for training and incorporating techniques like ReLU activations and a new regularization method called dropout.
And it competed in the ImageNet challenge.
It didn't just compete, it blew the competition away. Its error rate on the classification task was around 15%, I believe. The next best entry, which wasn't a deep learning model, was way up at over 25% error.
Wow, that's a massive jump in performance.
It was staggering. It was the proof point the field needed. It showed, unequivocally, that deep CNNs trained on large data sets with sufficient compute were the way forward for computer vision. It really ignited the modern deep learning explosion. After AlexNet, almost everyone in computer vision switched to using deep learning.
So AlexNet proved that going deeper worked. The natural next step was go even deeper.
Exactly. Researchers started pushing the boundaries, building networks with more and more layers, VGGNet, GoogleNet, or Inception. They believed deeper networks could learn more complex feature hierarchies and achieve better accuracy.
But it wasn't quite that simple, was it? Didn't they run into new problems?
They did. As networks got extremely deep, say dozens or even over 100 layers, training became incredibly difficult again. One major issue was the vanishing gradient problem we touched on.
The air signal getting weaker as it goes back.
Right. In very deep networks, the gradient signal could become so tiny by the time it reached the early layers that those layers essentially stopped learning effectively. There was also a related issue called the degradation problem. Counterintuitively, simply stacking more layers onto an already deep network could actually make its performance worse, both on the training data and in testing. The deeper network struggled to even learn the identity function, meaning it couldn't just pass the input through unchanged if needed.
So just adding layers wasn't the answer. How did they get around that? This is where another landmark architecture comes in, ResNet, which stands for Residual Network, developed by K-Ming Means and his colleagues at Microsoft Research.
A brilliant innovation.
The key idea in ResNet was the introduction of residual connections, or sometimes called skip connections.
Instead of forcing the signal to pass sequentially through every single layer, a skipped connection creates a shortcut. It takes the output from an earlier layer and adds it directly to the output of a later layer, bypassing one or more layers in between.
Like building an express lane on a highway.
Kind of, or like adding scaffolding, as you said earlier. What this does is allow the network to easily learn an identity mapping. If an intermediate block of layers isn't helpful, the network can just learn to make its output close to zero, and the signal effectively passes through the skip connection unchanged.
So it makes it easier for layers to just get out of the way if they're not needed.
Precisely. This simple trick dramatically eased the training of very deep networks. It overcame both the vanishing gradient and degradation problems, allowing researchers to successfully train networks with hundreds, even over 1,000 layers deep, and consistently achieve better performance with increased depth.
ResNet was hugely influential then. It really unlocked the potential of truly deep architectures.
Absolutely. ResNet, along with architectures like VGG, Inception, GoogleNet, and later DenseNet, really pushed the boundaries of depth and complexity, leading to massive gains in accuracy on benchmarks like ImageNet.
Were there other ways people tried to scale these networks besides just depth?
Yes, definitely. Depth was one dimension, but people also explored width, more filters per layer, and image resolution. Finding the right balance became key. This led to research into more efficient scaling strategies. Some involved automated methods like neural architecture search or NAS, where algorithms are actually used to search for the best network structure automatically. It's like AI designing AI.
Wow.
And there were also clever human-designed approaches like EfficientNet and RegNet, which proposed principled ways to scale up network depth, width, and resolution together in a balanced manner to maximize accuracy for a given computational budget.
And you mentioned normalization techniques being important, like batch normalization.
Oh, hugely important, often underappreciated, but absolutely critical. Batch normalization, introduced by Ioffe and Szegedy, was a game changer for training deep networks stably and quickly. It works by normalizing the inputs to each layer during training, essentially rescaling them to have zero mean and unit variance for each mini batch of data.
Why does that help?
It helps combat a problem called internal covariate shift, where the distribution of layer inputs changes during training as the weights in previous layers are updated. This shifting distribution can make training unstable and slow. Batch norm stabilizes the learning process, allows for much higher learning rates, and acts as a regularizer, reducing the need for other techniques like dropout sometimes.
So it just makes the whole training process smoother and more robust.
Much smoother. Many of the successes we've talked about, ultra-deep ResNets, even transformers later on, would have been much harder, perhaps impossible, to achieve reliably without techniques like batch normalization. It's a foundational piece of the modern deep learning toolkit.
That's fascinating how these technical details are so crucial. What about making these powerful networks run on, say, a smartphone? They can't be huge ResNets, right?
Right. That's where efficient architectures like MobileNet come in. They're specifically designed for resource-constrained environments like mobile phones or embedded systems. They use clever building blocks to drastically reduce the number of parameters and computations while trying to maintain as much accuracy as possible.
How does he do that?
Yeah.
You mentioned some complex terms.
Yeah, the key ideas are things like depth-wise separable convolutions. Instead of a standard convolution that mixes spatial information and channel information together, these separate the process. First, a depth-wise convolution applies a single filter to each input channel independently, filtering spatially. Then, a point-wise convolution, which is just a one-by-one convolution, combines the outputs across channels.
The chef analogy, chopping each ingredient separately before mixing.
Exactly. It's much more computationally efficient. They also use things like inverted residual blocks and linear bottlenecks, essentially smart ways to manage the flow of information, expanding it only when needed to do complex processing and then compressing it again.
So they trade off a bit of accuracy for a lot of speed and efficiency.
Generally, yes, but they're remarkably effective. And MobileNet architectures often have width and resolution multipliers, allowing developers to easily scale the model down further if needed, making them super flexible for deployment.
Okay, so CNNs evolved rapidly, getting deeper, more efficient. But then something new came along, borrowing ideas from a different part of AI. Vision transformers.
Yes, vision transformers, or VITs. This was a really exciting development around 2020. It took the transformer architecture, which had completely revolutionized natural language processing.
The models behind things like ChatGPT.
Precisely those. VIT showed that this architecture could also be incredibly effective for computer vision, challenging the dominance of CNNs.
But transformers work on sequences, like sequences of words.
Yeah.
How do you apply that to an image?
The core idea in VIT is surprisingly simple. You split the image into a grid of fixed-size, non-overlapping patches. Think of chopping the image up into small squares like a mosaic. Then you treat each patch as if it were a token, analogous to a word in a sentence. You flatten each patch and linearly project it into an embedding vector.
So you turn the image into a sequence of patch embeddings.
Exactly. And then you feed this sequence of patch embeddings into a standard transformer encoder.
And the key part of the transformer is that attention mechanism.
Right. The self-attention mechanism is the heart of it. Unlike CNNs, which have a built-in bias towards local information due to the small convolutional filters, the attention mechanism in a VIT allows every patch to directly attend to or look at every other patch in the image, regardless of how far apart they are.
So it can learn relationships between distant parts of the image right from the start.
It can. It learns which patches are most relevant to understanding the content of any given patch. So, for instance, to understand a patch showing an ear, it might learn to strongly attend to patches showing the eyes, nose, and mouth, even if they're far away in the patch sequence.
You said you can think of it as treating an image like a sentence of patches.
That's a good way to conceptualize it. The model learns the grammar of the image, how the different parts, patches, relate to each other entirely through the attention mechanism and the training data. It doesn't have the built-in assumptions about locality that CNNs do.
And does it work as well as CNNs?
Remarkably well, especially when trained on very large data sets. VTTs have achieved state-of-the-art results on ImageNet and other benchmarks, sometimes even surpassing CNNs. It really showed that the transformer architecture is incredibly general and flexible. It's not just for language. It can work powerfully on any data you can represent as a sequence of embeddings, including vision. It was a major validation of the power of self-attention.
Okay, so we've traced the evolution from biological inspiration through LeNet, AlexNet, ResNet, and even these newer vision transformers. Let's talk about where we actually see these technologies in action today. Their impact is just huge, isn't it?
Oh, absolutely massive. They're embedded in countless applications, often working quietly behind the scenes.
Facial recognition is probably one of the most obvious examples for many people. Unlocking your phone with your face. That's very likely a CNN or something derived from it at work.
Definitely. It's used for identity verification, security systems, photo tagging on social media. It's become incredibly widespread. CNNs are very good at learning the unique discriminative features of a face that allow them to distinguish between individuals.
And it's used in more critical areas, too. I remember reading about law enforcement using facial recognition tech, like Clearview AI, to help solve cold cases, including really serious ones like child exploitation cases.
Yes, that's a powerful example of its potential application. The ability to match faces, even from potentially old or low-quality images, against vast databases can be a valuable tool in investigations.
Of course, that also brings up discussions about privacy and ethics, which is a whole other deep dive. But the capability itself, powered largely by CNNs, is undeniable.
Agreed. The technology itself is powerful, and its application raises important societal questions.
Beyond faces, another huge area is medical imaging. This seems like a field ripe for visual pattern recognition.
Absolutely transformative. CNNs are being used to analyze medical scans like X-rays, CT scans, MRIs, pathology slides, you name it. They've shown remarkable ability in tasks like detecting cancerous tumors, identifying diabetic retinopathy from eye scans, spotting anomalies in lung X-rays. In some specific, well-defined tasks, they can achieve accuracy levels comparable to or even exceeding human experts.
That's incredible, helping doctors diagnose diseases earlier or more accurately.
That's the goal. They can act as tireless assistants, screening vast numbers of images, highlighting potentially suspicious areas that a radiologist might then examine more closely. They can help reduce workload and potentially catch things that might be missed.
But it hasn't completely replaced radiologists, despite some predictions. You mentioned Jeff Hinton's 2016 comment about not needing to train them anymore.
Right, and that prediction hasn't come to pass and isn't likely to anytime soon. It turns out that radiologists, like many highly trained professionals, do far more than just pattern recognition on images.
There's context involved.
Immense context. They integrate the patient's history, symptoms, other test results. They communicate with other doctors. They handle ambiguity, make complex judgments, and understand the nuances of a particular case in a way current AI simply can't.
So AI is more of a powerful tool, an assistant, rather than a replacement in that field.
Exactly. It's about augmenting human expertise, making skilled professionals more effective and efficient, not replacing their judgment or the human element of care. It highlights both the power and the limitations of current AI.
Okay, that makes sense. What about self-driving cars? CNNs must be absolutely critical there. Foundational. They are literally the eyes of most autonomous vehicle systems. CNNs, often multiple specialized ones working together, are responsible for the car's perception system.
What does that involve?
Recognizing everything in the environment in real time. Identifying other vehicles, pedestrians, cyclists, traffic lights and their state, traffic signs, lane markings, road boundaries, potential hazards, all under constantly changing conditions, different weather, lighting, day, night.
It's an incredibly complex visual scene understanding problem.
It really is. And the CNNs need to do this incredibly quickly and reliably. They process feeds from multiple cameras, sometimes LiDAR and radar data too, fusing it all together to build a model of the world around the car so the planning system can decide how to navigate safely. Without advanced CNNs, autonomous driving as we know it wouldn't be feasible.
But it's still a really hard problem, right? Driving isn't just seeing.
Absolutely. While the perception systems powered by CNNs are getting remarkably good, driving involves prediction, planning, and handling unexpected edge cases. The AI systems for driving are very specialized. They're not intelligent in a general human sense. They're trained on vast amounts of driving data, but the real world can always throw something completely new at them.
Things you just can't anticipate in training or simulation.
Exactly. Weird road configurations, unusual human behavior, bizarre accidents. Ensuring safety in all possible scenarios remains a massive engineering and validation challenge, even with state-of-the-art perception. So while CNNs are essential, they're just one part of a very complex system.
And there are other applications too, maybe less headline grabbing but still important. You mentioned the Visual Genome Project earlier.
Right, that project, led by Fei Li, aimed to push beyond just naming objects in an image. It's about understanding the relationships between objects and their attributes, and the actions happening in the scene.
So not just mat, but cat sitting on mat.
Exactly. And maybe brown cat sitting on striped mat under window with sunlight.
Oof.
It's about building a much richer, structured, almost semantic understanding of the image content, getting closer to how humans interpret a scene.
That seems like a crucial step towards more general AI understanding, moving from just recognition to reasoning about the visual world.
Definitely. It reflects the ongoing quest in AI to move beyond simple pattern matching towards deeper comprehension and common sense reasoning, which is still a major frontier. #UpTD5, the enduring legacy and future outlook. So let's try and pull this all together. We've seen the history, the mechanics, the applications. Why are CNNs considered such a fundamentally important invention in the grand scheme of AI? What's their enduring legacy?
Well, I think fundamentally they provided the first truly practical and incredibly effective solution to the long-standing problem of machine vision. They cracked the code, so to speak, on how machines could learn to interpret complex visual data directly from pixels, overcoming the brittleness of older methods.
They just worked much, much better than anything before.
Dramatically better, and they did it by drawing inspiration from biology, using that hierarchical structure, learning simple features first, then combining them into more complex ones. This hierarchical feature learning turned out to be a remarkably powerful principle.
And does that principle have implications beyond just vision?
Many researchers believe so. The success of hierarchical learning in CNNs provides a compelling model for how more general AI systems might learn about the world. The idea of automatically discovering layers of abstraction, finding meaningful patterns and correlations in raw data, and building internal representations that support decision-making that seems like a general principle for intelligence, not just vision.
So CNNs didn't just solve vision. They offered clues about how to build intelligence more broadly.
That's certainly one perspective. They demonstrated a powerful learning paradigm, data-driven discovery of hierarchical representations. It set a direction for much of the subsequent deep learning research, influencing architectures and other domains like audio and even language to some extent, before transformers took over there.
And the field isn't standing still, right? Research keeps pushing forward.
Oh, absolutely. While supervised learning with CNNs and related architectures has been incredibly successful and driven huge economic value, many leading researchers feel the next big breakthroughs will come from moving beyond supervised learning.
Like Andrew Ng's focus on unsupervised learning.
Exactly. Andrew Ng and others see unsupervised learning, where the AI learns patterns and structure from data without needing explicit human labels for every single example, as potentially a key step towards artificial general intelligence, AGI. The idea is that most human and animal learning is unsupervised. We learn about the world largely by observing it, not by being told the correct label for every single thing we see or experience. A truly intelligent system should be able to do the same.
And Jan LeCun is big on self-supervised learning. How is that different?
Self-supervised learning is a specific type of unsupervised learning that's gained enormous traction. The core idea is to create the supervision signal from the data itself. For example, you might mask out part of an image and train the network to predict the missing part. Or you might show it the beginning of a video clip and ask it to predict the next few frames.
So it learns about the structure of the world by trying to predict parts of it.
Precisely. LeCun is particularly optimistic about building predictive world models this way. He argues that true intelligence requires agents that can predict the consequences of their actions and understand the underlying dynamics of their environment, essentially, having common sense. Self-supervised learning seems like a promising path towards building such models.
So the quest continues, moving towards machines that learn more like humans do, through observation and prediction.
That's a major driving force in AI research today, yes. Building on the foundations laid by breakthroughs like CNNs.
All these advancements, from machines learning to see with CNNs to these newer approaches, it really makes you think about what intelligence even means, doesn't it?
It certainly does. It forces us to constantly reevaluate our definitions.
I'm reminded of Alan Turing's prediction back in 1950. He speculated that by the end of the 20th century, we'd be able to talk about machines thinking without causing a big fuss.
And while maybe the timeline was optimistic, the general trend seems clear.
Yeah, CNNs enabling machines to perform complex visual tasks that previously only humans could do definitely contributes to that feeling, doesn't it? Seeing a car navigate traffic or an AI diagnose a disease, it feels like intelligent behavior, even if the underlying mechanism is different from ours.
It challenges our intuitions about what requires thought.
And it's not always about replacing humans. We're seeing more and more examples of human-AI collaboration being incredibly powerful.
Yes, that's a really important point. In many complex domains, creative writing, scientific research, strategic planning, even medical diagnosis, the best results often come from a human expert working with an AI tool.
The AI handles the massive data processing, pattern finding, or simulation, and the human provides the context, judgment, and direction.
Exactly. The AI augments human capabilities. We see this in vision, too. Think of a security analyst using AI to flag suspicious events in video feeds, or a designer using AI tools to generate visual concepts. It's often about partnership, amplifying what humans can do.
So looking back at our deep dive today, we started with that spark of inspiration from our own visual cortex. We saw Jan LeCun's pioneering Linnet lay the groundwork in the 90s. Then the ImageNet challenge acting as a catalyst, leading to the explosion with AlexNet, ResNet, and the whole deep learning revolution in vision. We unpack that fascinating hierarchical learning process, how CNNs build understanding from simple edges all the way up to complex objects, almost like magic. And we touched on their undeniable impact everywhere, from your phone's facial recognition to helping doctors read scans to being the eyes of self-driving cars.
It's been quite a journey, and I think the success of CNNs leaves us with a really provocative thought. If machines can learn to process visual information in such sophisticated hierarchical ways, effectively learning to see and interpret the world, even discovering high-level concepts on their own, well, what other fundamental aspects of human cognition might be next? What other parts of our intelligence, maybe things we currently consider uniquely human, might eventually be understood and replicated through similar computational models, learning patterns from vast amounts of data? It really encourages you, the listener, to think about your own perception, that effortless way you see the world right now. Maybe understanding how these artificial systems work gives you a new appreciation or even a new perspective on the incredible complexity happening inside your own head every single second. Perhaps you'll start seeing the layers too.